Welcome to the course on design of reinforced concrete element. In this session, we are going to see about the assumption of limit state method, stress strain relationship for concrete, stress strain relationship for steel, and analysis of a singly reinforced beam. So first one, assumption of limit state method. This assumption is given in our IS codal provision, the page number 69, class 38.1. Limit state of collapse, flexure. Assumption is given in class 38.1. All the assumption is given here. The design for limit state of collapse in flexure shall be based on the assumption given below. Plane section normal to the axis remain plane after bending. So first assumption is, here it is, the first assumption is given. And the second one is, first assumption is, this one is here. The plane section normal to the axis remain plane after bending. The same assumptions we are following in the working stress concept also. The second one is maximum strain in concrete at the outermost compression fiber is 0.0035 in bending. The next one is here, the relationship between compressive stress distribution in concrete and the strain in concrete may be assumed to be a rectangle, trapezoidal and parabola, or any other shape which results in prediction of strength of substantial agreement with the results of the test. An acceptable stress strain curve is given in the figure 21. We will discuss later. So this is your stress curve. So in our codal provision, stress block is, we have to consider as your parabolic curve. But the stress curve is may be assumed. Compressive stress distribution in concrete and strain in concrete may be assumed to be a rectangle or trapezoidal or parabola. But our codal provision is assumed to be a parabolic stress block we have considered. For the design purposes, the concrete compressive strength of the concrete in the structures shall be assumed 0.67 times of characteristic strength, 0.67 FCK. The characteristic compressive strength of concrete only 67% we have considered. And the partial safety factor for concrete is 1.5 shall be applied in addition to this. This is all we will discuss the later. And the next one is here. The tensile strength of the concrete is ignored. The same assumptions we have followed in the working stress concept also. The next one is stress strain distribution are derived from the representative stress strain curve for the type of steels. The typical curves are given in the figure 23. So the first, this curve is a stress strain curve for concrete. So this only we have to consider as a 67% of FCK, and we will apply the partial safety factor for design purposes. This is for the stress strain curve for concrete. This is for the stress strain curve for steel. Figure 23, representative stress strain curve for reinforcement. So the assumption, one of the assumption is stresses in reinforcement are derived from the representative stress strain curve for the type of steel. For design purposes, partial safety factors 1.15 shall be applied. The maximum strain in tension reinforcement in the section at the failure stage, the strain in steel equal to Fy divided by 1.15 ES plus 0.002. Fy means, characteristic strength of the steel, and modulus of AS is a modulus of elasticity. So the stress block parameters and the stress strain curve for concrete and the stress strain curve for steel, cold formed steel, and stress strain curve for the definite yield point. So this is all the details are given in the IS 456. And okay, next one. So this assumption is we have discussed as per the codal provision IS 456. First one is a plane section remain plane after bending, and strain diagram is linear. Stress diagram is here partially parabolic and rectangular. So up to this is here parabolic. Up to this is parabolic and rectangular. The remaining part is rectangular. So we have to assume the strain diagram is linear, but this is a strain diagram. The first one is a strain diagram and this is a stress diagram. So stress diagram, strain is a linear, we have assuming. Stress diagram is a partially parabolic and rectangular. We will discuss later why we have to consider like this. And another one assumption is already we have discussed maximum strain in concrete. Maximum strain in concrete, this is a 0.0035. In bending, the maximum strain in steel also we have discussed. FY divided by 1.15 ES plus 0.002. So this is a maximum strain in steel. This is a maximum strain in concrete. At the stage of failure, the maximum strain in concrete is 0.0035. The next assumption is that the relationship between stress strain distribution. Concrete is assumed parabolic and maximum compressive stress is equal to 0.45 FCK. So this is your maximum compressive stress equal to 0.67 FCK divided by partial safety factor. Then we can get a 0.446 FCK or approximately 0.45 FCK is your maximum compressive stress. And another one assumption is tensile strength of the concrete is neglected and maximum strain in tension reinforcement at this in the section at failure should not be less than 0.87 Fy divided by ES plus 0.002 or otherwise Fy divided by 1.15 ES plus 0.002. So this is your maximum strain tension reinforcement. So here it is. Here it is this value. Here this value. Maximum strain in concrete, maximum strain in steel. Okay. Then this is a stress block and the resultant compressive force, resultant tensile force, both are acting in the opposite directions. Okay, both are acting in the opposite directions. So C act in these directions and T act in these directions. Stress strain relationship for concrete. The stress strain relationship, this figure is given in our IS 456. So the strain up to 0.002, the stress is a parabolic in nature. And beyond that strain 0.0035, from 0.002, the stress is here linear. So that's why we have considered in our stress block is parabolic. Parabolic we have considered. That's why our stress block is we have to consider as here parabolic in nature. The strain is up to the 0.002. This is here up to the 0.002. The stress is in parabolic in nature. Then from 0.002 to 0.0035, the stress is in a straight line. So that's why we have to consider our stress block is parabolic, partially parabolic and rectangular. So up to this strain, the stress is parabolic. Beyond the stress is your linear. The first curve is representing for the FCK is the idealized curve for concrete in Q. The first one is your idealized curve for concrete in Q. The second, this curve, idealized curve for concrete in structures. So 2/3 of FCK only we can get the field. So this curve is meant idealized curve for concrete in structures, but the design curve, this is the design curve. We are applying a partial safety factor, then we can get a 0.45 FCK. So the maximum compressive stress in concrete is, for the design purposes, we have to consider 45% of the FCK at the outermost compression fiber. So this is the maximum compressive strength. This value is taken from this curve. After applying partial safety for concrete, we can get the 0.45% of the 45% of the FCK. For the design purpose, the compressive strength of the concrete in structure is taken as, actually the characteristic compressive strength of the concrete is FCK, but in the structure is 2/3 of FCK, but in the design is 2/3 of FCK divided by partial safety factor 1.5. So the first curve, this is the first curve, this is the second curve, the last curve is a 0.45 FCK after applying the partial safety factor. So these details is given here, and partial safety factor is 1.5 applied in addition to this 0.67 factor. And this is already explained. The initial portion of the curve is a parabolic. After the strain 0.002, the stress becomes constant with increasing a load until the strain 0.0035 is reached. Here the concrete is assumed to have the failure. The strain diagram is this one. The stress block is, here it is. So this is the neutral axis. This is the neutral axis. Okay. Up to the 0.002 strain, the stress is here linear. The maximum strain is 0.0035. The maximum compressive stress is 0.45 FCK. So this is the stress strain curve for mild steel. This is already discussed as per the codal provision IS 456. So this is the characteristic curve. First one is a characteristic curve. Then after applying partial safety factors for steel 1.15, we can get 0.87 times of F. 87% of the characteristic strength of the steel we have considered as here, considered for the design purposes. This curve is for the stress strain curve for high strength deformed bars. Fe 415 steel and Fe 415 and Fe 500. The first dotted line is a characteristic curve. But for design purposes, we have to consider the partial safety factor. Analysis of your singly reinforced beam. This is your overall depth of the beam, breadth of the beam, effective depth of the beam. Effective depth of the beam means from the top of the compression fiber to center of the reinforcement. So this is the effective depth of the beam section, and this is your strain diagram. This is the stress diagram. In the strain diagram, we know already we discussed the maximum strain in concrete is 0.0035. At the time, the maximum compressive stress is 0.446 or 0.45 FCK. And up to the strain is, actually the stress and the strain in the neutral axis is 0 and gradually increasing from 0 to 0.002. At the time, the stress is a parabolic in nature. So this is a stress diagram, this is a strain diagram. Already we discussed maximum strain in steel is 0.87 Fy divided by ES. Here it is ES plus 0.002. Using this similar triangle concept, this is a depth of neutral axis. Depth of neutral axis. This is the depth of neutral axis XU. So XU, this is the X1. So using the similar triangle concept, this is the X1. Using the similar triangle concept, XU divided by 0.0035. We are considering upper triangle only. This is the neutral axis. This is the neutral axis. Up to this X1. This strain is 0.002. This one is your XU, depth of neutral axis. So here it is 0.0035. So using this similar triangle concept, X1 divided by 0.002, XU divided by 0.003. So solving this one, we can find out the value of X1 and X2. X1 and X2. Suppose this is X1 and this is a X2. So solving this one, we can get the value of X1 and X2. X1 is a 4 by 7. This is a 4 by 7. This is a 3 by 7. So adding these two values, we can get a total value. So XU equal to X1 plus X2. So X1 equal to 4 by 7. 4 by 7 plus 3 by 7. So we can get your 4 by 7 of XU, 3 by 7 of XU. So solving this, we can get a total value XU. So using the similar triangle concept, we can find out the value of X1 value and X2 value. The next one is a strain distribution. Assumption 1, the limit state theory gives a linear strain distribution across the cross section. Linear strain distribution across the cross section. So the linear strain distribution across the cross section, it varies as 0 at the neutral axis and maximum at the extreme fiber. Both tension and compressions, we can get a maximum strain. So maximum at the extreme fiber. So strain at the neutral axis is 0. The maximum or ultimate strain in concrete at the extreme equal to 0.0035. This is already we have discussed. And strain at a constant stress 0.00 FCK. Strain at the constant stress at the this one up to the 0.002. We can get a stress is a parabolic, and beyond that the stress is a linear. Ultimate strain in steel corresponding to maximum stress at the failure 0.87 Fy divided by S plus 0.002. So this is the maximum strain in steel. This is the stress diagram, strain diagram. This is the stress diagram. So both are acting, here it is the correctly mentioned, both are acting in the opposite directions. C is a compressive force, T is a tensile force. So this is a stress diagram, strain and stress diagram. Next one is a stress distribution. Our codal provision, the stress block we have assumed parabolic and partially parabolic and partially rectangle. Rectangle and partially parabolic we have to consider as your stress distribution. It has a parabolic shape from A to B. A to B is a parabolic shape. Then linear from B to C above the neutral axis. The various salient points of the stress diagram, stress at neutral axis is 0 and stress at point 002 strain is 0.67 FCK divided by 1.15, 0.45 FCK. And the stress at the extreme fiber is here 0.446 FCK. The strain at this level also 0.002 strain also the stress is here 0.446 FCK. And below the neutral axis the concrete is assumed to be cracked and the maximum stress in steel equal to Fy divided by 0.87 Fy. Stress block parameters. Area of the stress block equal to 0.36 FCK XU. So this value, area of the stress block means this area. So we have to consider the rectangle portion and the parabolic portions. So we will arrive like this. First one, area of the whole rectangle. Whole rectangle means 0.45 FCK multiplied by the XU. So total area of the totally we have to consider as a rectangle. Then deduct these portions. So minus of 1/3 of FCK, 1/3 of area, 1/3 of FCK. So this value also 0.45 FCK. So 0.45 FCK and multiplied by this distance multiplied by this distance. So 4/7 XU. So solving this one we can get the 0.36 FCK XU. So this is the area of the stress block. So totally we have to consider as a rectangle this area minus of this parabolic area we have deducted 1/3 of FCK and this height multiplied by the. So this is the area of the stress block 0.36 FCK into XU. Depth of center of compressive force from the extreme fiber is 0.42 XU. This is acting at a distance of 0.42 XU. 0.42 XU means this distance 3/7. 3/7 from the top of the compressive fiber. This is acting at the center of the compressive force from the extreme fiber in the compressions. 0.42 XU. Then a neutral axis depth. The neutral axis is the axis at which the stresses is 0. Both are stress and strain is 0 and it is situated at the center of gravity of the section. The depth of neutral axis for the singly reinforced beam is calculated by taking a equilibrium of tensile force and compressive force. Equilibrium of tensile force and compressive force. So this is the tensile force. T equal to area of the stress block 0.36 FCK and multiplied by the area B into XU. B into XU. This one, this area we have multiplied. B, this is a breadth of the section and XU is already having the area of the stress block. So 0.36 B into XU. This is your compressive force. This is your compressive force. Similarly, tensile force is your stress in the area. So 87% of the yield stress we have to consider and multiplied by the AST. So T equal to, already we know that from the, as per the codal provisions, Fy divided by partial safety factor for steel 1.15. This we can get 0.87 Fy. So for design purposes, we have to consider the 87% of the characteristic strength of the steel. So 87% of the Fy multiplied by the AST. So this is the T value, C and T. Depth of neutral axis for a singly reinforced beam is calculated by taking equilibrium of tensile and compressive forces. When we equating these two values, we can get the depth of neutral axis. B is here width of the section. D is here effective depth of the section. Area AST is area of the steel reinforcement. XU is a depth of neutral axis. C total compression and T equal to total tension. Equating for equilibrium of forces, compressive forces equal to tensile force. Total tension equal to total compressions. C equal to T or T equal to C. Compressive force equal to 0.36 FCK B into XU. Tensile force equal to 0.87 Fy AST. We want to calculate the depth of neutral axis. So XU we have to keep the left. XU equal to 0.87 Fy AST divided by 0.36 FCK B. As per the class, as per the IS codal provision, suppose if you want to XU by D equal to 0.87 Fy AST divided by 0.36 FCK B into D. So both sides we are divided by effective depth of the section. This is the actual neutral axis. This is the actual neutral axis. XU. And next one is here limiting depth of the neutral axis. The maximum strain in concrete is 0.0035 as per the code. The strain in steel at the failure should not be less than 0.87 Fy divided by ES plus 0.002. This is the maximum strain in steel. This is the maximum strain in concrete. From the similar triangle concept, this is the maximum limiting depth of neutral axis. So here it is here XU max. The depth of neutral axis we have to consider as XU max. So XU max 0.0, from the similar triangle concept, the same thing, 0.0035 divided by XU max and 0.87 Fy divided by ES plus 0.002 divided by D minus X. The remaining distance is D minus XU max. So using the similar triangle concept, we can write like this and keep the neutral axis values the left. So XU max divided by D minus XU max, it is equal to 0.0035 divided by 0.8. Rearrange this equation, that's all. So using this expression, we can find out the maximum depth of neutral axis. The next one is a moment of resistance. So moment of resistance equal to M equal to compressive forces in the Leverarm, M equal to tensile forces in the Leverarm. So Leverarm means the distance between compressive force to tensile forces. So Leverarm means the distance between the compressive force to tensile forces. So Leverarm D minus 0.42 XU. D minus 0.42 XU. So Leverarm equal to this one. Total depth is here, this is the effective depth of the section, and we know the compressive stress is acting at a distance of 0.4 to XU. So Leverarm equal to D minus 0.4 to XU. So moment of resistance equal to 0.36 FCK. Compressive force you know 0.36 FCK B into XU. So this is a compressive force multiplied by D minus 0.4 to XU. Leverarm. Similarly, for tensile force, moment equal to the tensile force equal to 0.87 Fy AST. So this is a tensile force multiplied by the Leverarm, D minus 0.4 to XU. Then limited value of moment of resistance. Limiting depth of neutral axis, already we discussed from the similar triangle concept. This is a 0.0035. This is 0.87 Fy divided by S plus 0.002. So using the similar triangle concept, and XU max, we can keep the XU max equal to XU max divided by D minus XU max 0.0035 divided by strain in steel is 0.87 Fy divided by Es plus 0.002. So solving this one, XU max multiplied by this 0.87 Fy divided by Es plus 0.002 equal to equal to 0.0035 multiplied by the D minus XU max. So solving this equation, XU max maximum depth of neutral axis divided by D equal to 0.0035 divided by 0.87 Fy divided by Es plus 0.002. Solving this one, 0.0055. 0.0055. So here it is, these two values, if you know the yield strength of the steel and Young's modulus of the steel equal to commonly 2 into 10 power of 5 Newton per mm squared, and Fy equal to maybe 250 grade and 415 grade or 500 grade. So after substituting this value, we can get your maximum depth of neutral axis for the different grade of steel. For substituting different grade of steel, 250, 415, 500, we can get your maximum depth of neutral axis. For this one is 0.53, this one is your 0.48 and 0.46. For Fy 415 grade of steel, XU max by D equal to 0.48. For 500 is 0.46. So these details are given. Young's modulus is common, equal to 2 into 10 power of 5 Newton per mm squared. And so substituting these two values, Fy and Es, in the above equation, the previous equation, we can find out the xu max by d value. This is given in our IS codal provisions. The page number 70, the limiting value of depth of neutral axis for the different grade of steel based on the assumptions Fy and xu max by d. For 250 grade of steel 0.53, 415 0.48 and 500 is 0.46. So this is given in the page number 70 IS 456 2000. This is the maximum depth of neutral axis. The next one is a percentage of steel. Percentage of tensile reinforcement can be found by equating tensile and compressive forces. So tensile force equal to 0.87 Fy AST and compressive force is 0.36 FCK B into XU. Rearrange this above two equation. Area of the steel divided by breadth of the section equal to 0.36 FCK XU divided by 0.87 Fy. But percentage of the steel means PT equal to area of the steel divided by cross section B into D. So we want this like this one, AST divided by BD. So AST divided by BD and multiplied by the D terms in the both of the equations. So 0.36 FCK XU divided by 0.87 Fy into D multiplied by the D. And as the value x by D is limited, suppose the XU by D is limited, the maximum value is given, the maximum percentage of the steel. So PT in percentage of steel equal to 0.36 FCK, the same equations multiplied by the XU max into 100. XU by D multiplied by the XU max into 100. Percentage of steel for maximum. So XU by D, instead of XU by D, we can substitute the value of XU max by D. So we can write this equation, the maximum depth of maximum percentage of the steel. So XU by D, instead of this value, we can substitute the XU max by D. So for mild steel value, already we know that XU max by D equal to 0.53 and the yield stress is 250 Newton per mm square. So putting this value, we know the value of XU max by D. So after substituting this 1% of the steel equal to, for Fe 250 grade of steel, percentage of the steel is 0.008. In this equation, substitute the value of FCK, grade of concrete, and characteristic strength of the concrete and the characteristic strength of the steel, and corresponding maximum depth of XU max by D value, then we can get your maximum percentage of the tensile reinforcement. Thank you.